nuclear properties, the deuterium, nuclear core, and I'm going to see how far we can go. But then I'm going to be doing also questions, and then you can also interact, or if you have some ideas, you can also say whatever you like to say related with that. Okay, the first thing is the discovery of the neutron. In 1911, Rutherford proposed the atomic structure with massive nucleus, but this nucleus was having only the protons in the center. Then the idea was electrons surrounding the nucleus, that the nucleus was only protons. But then scientists, they realized that something was missing in all the idea, because when they doing the experiment, they were realized that the helium, in comparison with the hydrogen, was not having the same balance. Then they were always asking what happened. Yeah? Then what happened in that case? What do you think? What is missing in the Rutherford idea? The thing that is missing are the neutrons, because in the center is not only protons. We had the protons and we had also the neutrons. Then, later in 1932, Darwin and his collaborator, they began to do some series of experiments, and actually they found the neutrons. And they came out with a new idea where we had the protons, the neutrons, and the electrons that were surrounding all the nucleus. But then was a new question. Okay, in the nucleus we had the protons and the neutrons. Why the electrons are not also in the nucleus? What do you see? Why the electrons keep this distance from the nucleus? What kind of thing made there stay some distance far and not collapsing or something? Okay, as we see, we have three principal reasons. The first one is the nuclear sign. According to the uncertainty principles that say that we cannot have a maximum relation, we had the variation of the distance related with the variation of the speed related with the momentum. Then, if you do the substitution of the distance for the nucleus and begin to find out how much needs to be the speed of the electron to be in the nucleus, you are going to find that the speed needs to be higher of the speed of the light. Then it's something that is not possible. This means that we had some limits in the kinetic energy of the electrons. And this is what also doesn't allow the protons and the electrons collapse or create this massive nucleus. And also, you know, they had different charge, and then we had the distance. The other thing is the nuclear spin. When they were doing some experiment with deuterium, also they see how the protons as electrons, that they had the different variation when they had two protons and one electron, how if we had the three fermions, must result in a total spin that is half of the spin. But this was not observed in the experiment. The experiment where showed that needs to be one. Then actually this is another reason why it cannot happen. And the other reason is the nuclear magnetic momentum. The electron is moving so fast. It's moving 1,000 times faster than the proton in the nucleus. Then you can identify independently, and you can see that this independency also doesn't allow him to stay in the nucleus with the proton and the neutrons in the same time. Okay, with all this idea, then for the scientists was kind of clear that it's some rules that are giving all this systematic system. Then after that, in 1930, before they defined exactly the neutron, some other scientists in Germany, Becker, they were doing some nice experiment. If we see here, we had some alpha particles. Then they had the idea to have these alpha particles bombing some force of beryllium that is here. And then what happened after that? After that, we had that the radiation that is released is going. Then they were asking to themselves, what happened? Why after we bombing beryllium, or you can use other like boron, you can see that there's some radiation. Then they were asking, why is the radiation, why this means this radiation? They trying to see if the radiation has some charge, or how is the behavior. Then they notice that doesn't have charge. This means cannot be proton, cannot be electron, because the proton and the electron have charge. And they will say, come on, it's something else, something that doesn't have charge. But actually it needs to be something strong because it's energy, then it's bombing, it's not stronger to move the star. Then they need to be something else. Then they were doing their research and trying to figure out what is that. Then they were playing with other foils because every time they were trying to play for so many years and trying to identify this unknown radiation and what is causing that. And then they put also paraffin that actually is like wax paper in this case, but then they call it paraffin. And they discovered that after that they find a proton that they were moving with 5.7 mega electron volt. That is slow, it's a lot of energy. Then they say, okay, something is going on. But until now, nobody really understands what is happening, but everybody was curious to understand what is happening inside. They also say that later, in 1932, Chalwin finally proposed one idea. He used practically the same setup of the experiment. Here we had a source of polonium. We had the alpha particle that are bombing the beryllium. We had the radiation that until now not everybody really know what will happen. And then he put also the paraffin and he observed the protons. Okay, then he said something. Okay, what's happened with this system? We have no charge. This is the radiation that we have no charge here. Yeah? Okay, something that doesn't have charge. But need to be strong enough to take out the protons. Then he was saying, is the alpha particle are super small in comparison with the proton. Then he said, come on, cannot be the alpha because they don't really have all this energy. And then it's not going to be enough to take out the proton. Then the proton is not going to move. Need to be something that has practically the same size and has the same mass. Yeah, then they need something that has the same mass as the proton, but doesn't have charge. Then something that is there in the nucleus also. Then they call this the neutron. Then this was the first time that they understand, okay, something is there. Oh, and they also find the mass. The mass of the neutrons is, the first time was 1.00 and 1.00 U. That later, other people do the same experiment with more precision, and they find that in the model, with the model technique, they found that the mass is 1.0087 U. This means was not really that far from the value that was found. And also, with all these measurements, they were able to identify the gamma radiation that is coming when the proton and the neutron are dissociated. When they are going, then as answer or a response for this is the gamma radiation. Then it's kind of interesting, the way that they do this experiment, because after that came a lot of nice ideas about how to do the organization of the chemical elements and understand them. Then one of the first things that we need to see is here. For example, we had the protons and the neutrons. The proton has the charge, and actually the proton is going to give all the characteristics of the chemical compounds. Yeah, and here we had different consequences to the discovery of the neutron. One of these is, for example, that the hydrogen can be had different variation. We can have one hydrogen that had only one proton, or we can have the deuterium that is again hydrogen but has also one neutron. Then we're going to have one proton and one neutron. And another variation is the proton with two neutrons. Then we had this variation that is the tritium, when we had the two neutrons and the proton. Okay, then when this kind of variation happens, they call this the isotopes. In this case, the hydrogen isotopes. Okay, and with this determination, then we can have a description about how are the elements in the chemicals. We can describe this element using the atomic number Z, that is the number of proton, N is the neutron number, that is the number of neutron, A, the mass number, that is the sum to the number of proton plus the number of neutron, and we have the chemical element symbol. Then we can represent this in this form in general. Then, for example, we can have the lithium in their different isotopes, when we had here 3, that is the number of proton. Here we had the number of neutrons and the total atomic sum, that is C plus N, that is giving this number that we see in so many cases. Any question until now? Okay.
The bottom left is proton. The bottom right is proton. The bottom left.
Oh, you can see. C is this, then is the number of proton. This means this is the number of proton. This represents the number of neutrons, and this is the sum proton plus neutron. The total number is you do the sum for both of these. Yeah? Okay. Then is we notice how the discoveries the neutron actually open a lot of information about how the chemical are inside. Then another variation that we can see is that all the characteristics for the chemical element actually are in the C number. And the dependence of the chemical also doesn't really depend too much of the neutron, depends more of the proton and of the electron. But the neutrons are gonna give different variation in the different species that we find related with the chemicals. Here, for example, we had the isotones. The isotones, if you see, is the case when we had different chemicals, for example, different elements, yeah, but the numbers of neutrons are the same. Then they are isotones. They can be different chemical elements, but they have exactly the same number of neutrons. Or we can have something that we call isobars, that the isobars have the total number, that is the proton plus neutrons, exactly the same. Then, for example, the xenon and the E, that is going to give us this kind of classification. Okay, but then after that is coming more interesting thing, because it's not also giving us organization about how everything is in the chemicals. Also it's giving us information about what is the mass, what is the energy, and how they are acting. For example, the proton, we identify the proton by P, the neutron by N, and the electron by E. They had their own rest energy. You can see that the proton and the neutron has a really high energy. This is something that is stable in the nucleus. And if you see the electron has really little quantity because it's moving all the time, then we see that the one that is moving and do all the transporting is the electrons. We had the charge, the proton, it has plus E charge, the neutron 0 charge, and the electron minus E. Then we had the mass. We see how the proton and the neutron had a really huge mass, but the electron is very small and doesn't really have too much mass. And we had the spins. The spin of the proton, the neutron, and electron is 1/2, and the moment magnetic is 2.79 for the proton, minus 1.91 for the neutron, and minus 1.001 for the electron. Okay, now what happened inside the proton and the neutron? This was another question that scientists were asking so many times. Like, okay, now we have information about how are the neutrons, the protons, the electrons, but is something else? Is something else inside? How we can understand this something? Then they continue doing experiments, and actually they found a collective inside the nucleus, and they found that is the proton and neutron are also constitute 4 particles called quarks. Then let me present to you the quarks. We have the up that is positive, has 2/3 charge. Down is minus 1/3. Yeah, then they had the charge. We had the strength is minus 1/3. Did everybody know why it's called strange?
No.
Okay, it's strange because they were doing some experiment with radiation, and they found that this one in particular were having a longer period of decay. Then they say, oh, it's strange. It's acting strange. No, it's not acting in the normal way. We had another that is called charm. Did somebody have any clue or can say something? Why it can be charm? Okay, they called charm because when they were doing the experiment, they were so fascinated. They were like, oh my God, like they were in something like, oh, was kind of magic. Then they decided to put the name charm. And then here we had the top. I don't know if somebody listen. The top and the bottom that actually are the kind of the one that are ruling so many things. Then they call, okay, are the top there like that. Then they put this number. Okay, but now what happened inside the proton and the neutron? In the proton and neutron, we had the up and down. Actually, up because the charge is positive and down is negative. Then the proton actually had 2 ups and 1 down. And the neutron had 2 down and 1 up. Then, if you see, for example, with the neutron, in the neutron we had down, down, up. How much is the total charge? It's 0, exactly. So then correspond. Then we will see how they represent. And how about the proton? Then we had 2 ups and 1 down. Then we had charge that is exactly plus 1, that is 1 plus the electron charge